Hello everyone, today we will learn the properties of sine function and cosine function. Through the previous study of exponential function and logarithmic function, we know that the research ideas of function properties can be completed according to the steps of drawing function images, observing images, discovering properties and proving properties. In the last lesson, we have learned the images of sine function and cosine function. In this lesson, let's use the function image to explore its properties. When it comes to the properties of functions, please compare the previous research on the properties of functions. What properties of sine function and cosine function can be studied in this lesson? According to the experience of studying function, we know that we can study its definition domain, value domain, parity, monotonicity, maximum and minimum. The number to nature refers to the characteristics of the research object that remain unchanged in the process of change. Next, please observe the image of sine function and consider the features of sine function that remain unchanged in combination with its own characteristics. If you observe the image, you will find that the image from 0 to 2 pi shifts left or right, and the unit of 2 pi is the same image in the negative to pi to 0 and 2 pi to 4 pi. In other words, points with the same ordinate will appear every to pi or negative to pi in the abscissa. On this basis, if I continue to shift the image to the left or right, I will find that the image presents this cycle of changes, that is to say, when the abscissa is every 4 pi or negative 4 pi unit length, the ordinate will also be the same. Then from 2 pi or negative to pi to 4 pi or negative 4 pi, and so on, we will find. When the abscissa is every to k pi, where k is the unit length of an integer, points with the same ordinate will appear. By observing the function image, we get the above conjecture. Now please think about how to explain the above conjecture with algebraic methods. Just through observation, we can find that the image of sine function satisfies that when the value of independent variable x increases by an integer multiple of 2 pi, the corresponding function value is the same as that of x. From the perspective of algebra, we can prove that sine x plus 2k pi equals sine x by using the induction formula. According to this formula, when k takes 1, the formula becomes that sine x plus 2 pi equals sine x, that is, the function value of x plus 2 pi is the same as x. Back to the image, it can be understood that the image on 0 to 2 pi and 2 pi to 4 pi is the same. In addition, if we take k as negative 1, we will find that this formula becomes sine x minus 2 pi equals sine x. That is, the function value of x minus 2 pi is the same as that of x. Then go back to the image, which means that the image from 0 to 2 pi is the same as the image from negative to pi to 0. Thus, the correspondence between number and shape is completed. With the above analysis process, answer the following questions. What is a periodic function? What is a cycle? In general, let the definition field of function fx be D. If there is a non-zero constant t such that for every x that belongs to D, x plus t belongs to D, and fx plus t equals fx, then function fx is called a periodic function, and the non-constant t is called the period of this function. When we look at this definition together, we will find that it has many restrictions. For example, the requirement for t is the existence of a non-zero constant, and the requirement for the independent variable x is everyone in the definition field. Then, through reading the relevant content, think about how you understand the existence of a non-zero constant in the definition. For a function fx, if for any non-zero constant t, it is always impossible to make fx plus t equal to fx constant. That is to say, such a value x0 can always be found in the fx definition field, so that x0 plus t is not equal to x0. In this case, we say that the function fx is not a periodic function. Therefore, to judge whether a function is a periodic function, it is required to find such a non-zero constant t that fx plus t equals fx constant. Then, with the above understanding of periodic functions, please consider whether sine functions are periodic functions. Obviously, sine function meets the requirements of periodic function. It is a periodic function. Then through calculation, we will find that sine to third of pi plus pi is equal to the negative to thirds root 3, which is the same as sine to third of pi. And sine 1/3 of pi plus 1/3 of pi equals 3/2 of the root 3 equals sine 1/3 of pi. Sine 4/3 pi plus 1/3 of pi equals negative 3/2 of the root 3 equals sine 4/3 pi. Then, according to the above calculation results, can we explain that 1/3 of pi is a period of sine function y equal to sine x? Why? If the third pi is the period of a function, then combined with the definition of periodic function, I know that for each x in the function definition domain, fx plus the third pi is equal to fx. In the definition of sine function, we can find a value, for example, x is equal to pi in 6. We find that 6 parts of pi plus 3 parts of pi is equal to 2 parts of pi, and the result is 1. It is different from the value of sine 1/6 of pi, so we say that 1/3 of pi is not a period of a sine function. We have just verified that sine function is a periodic function. Now please think about the period of sine function. From the definition of period, I know that the algebraic relationship it satisfies is that fx plus t equals fx, that is, the value of each self-variable x plus t in the definition field is constant. Then the induction formula sine x plus 2k pi equals sine x, where k is an integer. I know that the period of a sine function is 2k pi, where k is an integer and not 0. However, let's observe that with the different values of k, the period of the sine function is not unique. All integral multiples of 2 pi are its periods. That's like sine function. Let's go back to the general periodic function. For a general periodic function fx, if the constant t is the period of this function, can you prove that nt where n is an integer and not 0 is also its period? According to the definition of periodic function, if t is the period of a function, fx plus t equals fx for every x in the definition field. Next, I will write fx plus 2t in the form of fx plus t plus t. This is equivalent to saying that after the independent variable x plus t plus the period, its function value should be equal to the function value corresponding to x plus t, and then equal to fx plus t. And we know from the relationship that it is equal to fx. Let's see, fx plus 2t is equal to fx. I can know that 2t is also the period of this function. Therefore, I can deduce 3t for t or even nt, where n is a positive integer, which is its period. That's similar. If fx plus t equals fx, I can understand that the function value remains unchanged after the independent variable decreases t. Then I can write fx as equals fx minus t, and then I can write the independent variable reduction cycle t equals fx minus t. And this formula can be written as fx minus 2t. For x minus 2t, it is written as fx plus minus 2t. Then from fx equals fx plus minus 2t, I can know that negative 2t and negative 3t, negative for t and negative nt in turn, where n is a positive integer, which is one of its cycles, through the above two proofs. We will find that nt where n is an integer and not 0 is its period. From this derivation process, we will find that the period of a periodic function can be positive, negative, and unique. But please note that the above derivation process is based on if x is any real number in the definition field of the periodic function fx, then x plus t, x plus 2t, and x minus t must also be in the definition field of this function. Therefore, the definition domain of the periodic function fx must have neither the maximum nor the minimum of the business. Infinite. Next, please consider whether there is a minimum positive period in all periods of a sine function. The period of the sine function is 2k pi, where k is an integer and not 0. If we take k as 1, we will find that the smallest positive number is 2 pi. Like the sine function, if there is a minimum positive number in all the periods of the periodic function fx, then this minimum positive number is called the minimum positive period of fx. That is, 2 pi is the minimum positive period of the sine function. In the follow-up study, unless otherwise specified, the period involved generally refers to the minimum positive period of the function, because the minimum positive period is the most representative one. However, it should be noted that not all periodic functions have the minimum positive period. Next, please compare our study on the periodicity of sine function to consider whether the cosine function is a periodic function. If yes, please indicate its period and minimum positive period. By observing the image of cosine function and combining with the definition of periodic function, we know that cosine function is also a periodic function, and 2k pi, where k is an integer and not 0, is its period. Its minimum positive period is also 2 pi. Above we focus on the period of sine function and cosine function. Now please think about it. How can knowing the period of a function help us to study its image properties? The periodicity of functions can simplify our exploration of the image and properties of functions. If the period of a periodic function is known, then I can start from one period to explore its nature. As long as we know its image and properties in a cycle, its image and properties in the whole domain will be completely clear. In addition, taking sine function as an example, we know that 2 pi is its minimum positive period, so the research on it can not only start from the interval of 0 to 2 pi. As long as the unit of 2 pi is shifted from left to right, the obtained interval can be studied as one of its periods. On the basis of mastering the periodicity of sine function and cosine function, we will continue to explore other properties. Let's see whether the periodicity of a given function can simplify the process of exploring its properties. Now please observe the images of sine function and cosine function. Complete the following table. As we all know, the domain of sine function and cosine function is our value, and the domain is -1 to 1. But through the just learning, we know that their periods are 2k pi, where k is an integer and not 0. Next, we will observe the images of sine function and cosine function. We will find that sine function is symmetrical about the origin and cosine function is symmetrical about the y-axis. It is concluded that the sine function is an odd function and the cosine function is the first even function. We believe that the above properties can be completed quickly. The following properties, we will focus on the sine function to explore. Let's learn the properties of cosine function by analogy. As for the sine function, we just know that it is a periodic function, so we only need to start with one cycle of it, and then extend it to the properties of the whole domain. To explore the axis of symmetry and the center of symmetry, we should first know what is the axis of symmetry and what is the center of symmetry. The axis of symmetry is the vertical bisector of the line connecting the points of symmetry. The symmetry center is that the image rotates 180 degrees around this point and coincides with the original image. Now, please look at the image of the sine function and find the axis and center of symmetry from -half pi to 3 pi. Observing the image, we can find that on the interval from -half pi to 3 pi, the function is symmetrical about the three lines x equals -half pi, x equals 2 parts pi, and x equals 3 pi. If I continue to shift the unit of 2 pi to the left or right, I will find that the sine function is equal to -5 of pi with respect to x, -3 pi with respect to x, 5 of pi with respect to x, 7 of pi with respect to x, and so on. The straight lines are symmetrical, and these symmetrical lines differ by pi unit length on the basis of half pi. Then I can conclude that the axis of symmetry of the sine function is x equal to half pi plus k pi, where k is all lines of an integer. Then let's continue to look at the center of symmetry on this interval. It will be found that the image is coincident with the original image after rotating 180 degrees about 0, 0 and pi, 0. That is, 0, 0 and pi, 0 are the symmetry centers of sine functions. According to the induction just now, I can know that the symmetry center of the sine function is k, k0, where k is an integer. Please continue to observe the sine function image and explore the monotonicity of its function from -half pi to 3 pi. By observing the image of the function, I can find that when x increases from -half pi to half pi, the curve gradually rises and the function value increases from -1 to 1. When x increases from half pi to 3 pi, the curve gradually decreases and the function value decreases from 1 to -1. If I use a table to show the variation trend of sine function independent variable and function value, see the following figure. Looking at this table, we can clearly know that the sine function is monotonically increasing from -pi to pi. It is monotonically decreasing from half pi to 3 pi. Then, due to the periodicity of the sine function, I only need to add an integer multiple of the minimum positive period to pi to the endpoint to get each monotonic interval of the sine function in the domain. That is to say, the sine function is monotonically increasing in every closed interval from -half pi plus 2k pi to half pi plus 2k pi, where k is an integer. Its value increases from -1 to 1. In each closed interval, half pi plus 2k pi to 3 pi plus 2k pi, where k is an integer, is monotonically decreasing. Its value decreases from 1 to -1. Then complete the form ... In the process of exploring the monotonicity just now, it is easy to find. The sine function gets the maximum value of 1 only if x is equal to half pi plus 2k pi, where k is an integer, and gets the minimum value of -1 only if x is equal to -half pi plus 2k pi, where k is an integer. Then complete the form, after you have mastered the above process of exploring the properties of sine function. After class, please analogy the process of exploring the properties of sine function, explore the properties of cosine function, and complete the table. Above, we continue to explore the parity, symmetry, monotonicity, maximum and minimum of sine function and cosine function. Next, please answer the following questions. 1. How to prove the parity of sine function and cosine function? What is the help of knowing the parity of a function for studying its image and properties? 2. Which interval was chosen to study the monotonicity of sine function and cosine function respectively? Why? Parity of sine function and cosine function we can judge by observing the image. Then it is proved that sine negative x is equal to negative sine x and cosine negative x is equal to cosine x by using the induction formula. If I know the parity of a function, I know the symmetry of the image on both sides of the y-axis. As long as I explore the images and properties on one side, the images and properties on the whole definition will be clear. In the selection of interval, the sine number chooses negative half pi to 3 second pi, and the cosine function chooses negative pi to pi, which are their minimum positive periods. Moreover, the selected intervals are all near the outer axis, which is convenient to obtain the properties of the whole localized domain by means of periodic left or right translation. In this lesson, we have gone through the process of observing images, discovering properties, and proving properties. The periodicity, parity, symmetry, monotonicity, maximum and minimum of sine function and cosine function are explored. The general ideas and methods of studying the properties of functions are further realized. That's all for this class. Thank you for watching. Goodbye.